All right, so last PowerPoint. Last PowerPoint, we started talking about this this miracle, this gift from, again, I don't know if I want to use the word God, but this gift from this higher power, this thing that makes us think that maybe there's this order to the cosmos, right? Because it seems pretty crazy that this sort of universal law, right, which is what the central limit theorem is. It's like a law of gravity. It's a law of the universe. It can be proven mathematically. It could be shown empirically. Actually exists and allows us statistics, which in turn allows us, of course, a really incredible way, sort of mathematically defensible way of studying this exact universe that we're talking about. So last PowerPoint, we talked a lot about kind of big picture, what the central limit theorem is. This PowerPoint's going to be a little bit more focused on kind of a nuts and bolts, kind of hands-on approach to actually sort of using or implementing the central limit theorem. So, here's an example. Let's say that x, random variable, is the amount of soda in a randomly selected can of Pepsi. X, right, the amount of soda in just a single can of Pepsi, it's known to follow a normal distribution with a mean of 12 ounces and a standard deviation of 1 ounce, right? So cans of soda, say they have 12 ounces in them. If you measured that volume very precisely, would it be exactly 12 ounces? Actually, probably not. It would be very, very close to 12 because, right, their manufacturing plants are pretty finely tuned. But if you measured it precisely enough, you would see that there is a little bit of variation. Sometimes it's a little more than 12 ounces, sometimes it's a little less than 12 ounces, right? Again, all Pepsi's really saying is that on average you're going to get 12 ounces of soda in a can. Now, their standard deviation is probably something like 0.0001 ounce, right? Their standard deviation, like I said, is probably very small. 1 ounce is unrealistically large, but it's an easy number for us to work with in terms of this problem. Now, let's just start. This is a review problem. This is what? This is us limbering up a little bit so we don't hurt ourselves when we do some heavier lifting a little later in the PowerPoint. So, x is the amount of soda in a single can of Pepsi. What's the probability that that's between 11 and 13 ounces? Well, this is just a normal probability problem, just like we did whatever it was, 3 and 4, I think, PowerPoints ago. X follows a normal distribution, so it has that nice bell shape to it. Its mean is 12, so this thing is centered at 12. And I want the area, I want the probability of it being between 11 and 13. So that's normal CDF, LUMS, Lahore University of Managerial Sciences, where they actually cater in the middle of class. That is, you get a little app on your phone, and just in the middle of lecture, you can order whatever you want. You can order ice cream, you could order a ribeye steak, you could order pasta, lasagna, cupcakes. It's incredible. Lahore University Managerial Sciences. So, normal CDF, my lower, my leftmost bound is 11. My upper, my rightmost bound is 13. The mean is 12, and the standard deviation is 1. So again, just a review problem. If I put that in my calculator, verify that I get roughly 68%. Actually, that's what the empirical rule tells me, because I'm actually really just asking what's the probability that I'm within 1 standard deviation of the mean. Now, here's where the central limit theorem comes into play. Let's say that instead of 1 can of Pepsi, we get a 6-pack of Pepsi. And we chug the cans one after another. We measure the volume in each of the cans, and we actually compute the sample mean volume, the amount of soda, the average amount of soda in our sample of 6 cans. Let's say x bar is that sample mean. First off, what is the distribution of x bar? What do I know about the random variable that is the sample mean? Well, since I said on the previous slide that the underlying distribution was normal, we know that the sample mean x bar is normal. Anytime x is normal, x bar is always normal, regardless of sample size. Thanks, central limit theorem. The two other facts that we know, right? X bar is a random variable. We know it follows a normal distribution. Every normal distribution has a mean and standard deviation. What are they for this problem? Well, the mean of X bar is always going to be the mean of X, which we were told in our previous slide was 12. The standard deviation of X bar, right? This is one of those central limit theorem facts. You need to know it. You need to memorize it. Is the standard deviation of X over the square root of n. We were told in the previous slide the standard deviation was 1. We have a sample of size 6. So 1 over the square root of 6, a little bit of rounding, is 0.41. So I ask this question, a slightly different question. What is the probability that the sample mean is between 11 and 13? Well, it's just a normal problem, right? We said that X bar, the sample mean, follows a normal distribution. So it's a type of problem that I've already mastered, that I already know how to do. I draw my picture. The sample mean has a normal distribution, so it has that bell shape to it, centered at 12. I want the area probability between 11 and 13. So again, that's normal CDF. My leftmost bound is 11, my upper bound is 13, my mean is 12. Now, this is the probability of X bar, not X, so this is the one tweak. This is the one difference. The standard deviation is not 1. That was the standard deviation of X. We're dealing with X bar. We're dealing with the sample mean. The standard deviation of X bar, according to the central limit theorem, was 1 divided by the square root of 6, which was 0.41. So I got to plug that in for my standard deviation. If I do that, I get, right, roughly 98.5%. How do I interpret this? How do I take it beyond meaningless number crunching? Well, it actually has a very nice interpretation. I've been saying all along that the sample mean is our best guess for the true but often unknown population mean. If you were to ask me, why is it a good guess, I would answer your question in the following way. I would say, because it's very likely to be very close to the true mean. Now, you could counter. What could you counter with? You could say, well, tell me what you mean by very likely. Tell me what you mean by very close. The central limit theorem allows us to answer both of those questions very explicitly. In this example, if you asked me, right, what do I mean when I say it's very likely to be very close to the true mean, I would say that for a sample of size 6, for a 6-pack of soda, there is a 98.53% chance. That's pretty high. It's pretty close to 100. There's a 98.5% chance that the sample mean will be close to the true mean. How close? Within 1 ounce of the true mean. Why within 1 ounce? Well, remember, the problem we just solved was, right, the probability is between 11 and 13. The true mean is 12. So 11 and 13, right, are 1 away from 12. So I'm essentially asking, right, what's the probability it's within 1 ounce of the true mean? Now, maybe I'll do a little side PowerPoint here to elaborate on this fact, because it is fairly interesting. But again, I don't want the details and trying to wrestle with them take away from the big picture. But what's really exciting and what's really cool and what may or may not be obvious to you is that we could actually make this statement even if we did not know that the true mean was 12, right? Which is starting to get closer to, right, an actual useful way of using statistics, right? Up until now, we're always assuming. Let's assume we know that the population mean is this. Let's assume that the population mean of that. But the whole point of statistics is that we generally don't know what the population mean is. And even though in this problem we use the fact that we knew it's 12, I promise you that we could rephrase that problem in terms of z, in terms of standard deviations, and not have to know the mean and still get that 98.53% conclusion, right? So the central limit theorem allows us to make a very powerful observation. It allows us to very precisely and specifically quantify exactly how good the sample mean is going to be for a given sample size. Let's try another problem. What is the probability that the sample mean will be between 11.5 and 12.5 ounces? So now I'm asking, what's the probability that the sample mean is going to be within half an ounce of the true mean? Well, this is, again, it's just a normal probability problem. At this point, it should hopefully be becoming old hat for you. I drew the picture, I colored it in. It's going to be normal CDF, LUMS, Lahore University of Managerial Sciences in scenic upstate Pakistan. In this example, my leftmost bound is 11.5. My rightmost bound is 12.5. My mean is 12. And my standard deviation is 0.41. So I get about 77%, or actually if I were to bump it up, 78%. Again, how could I interpret this? For a sample of size 6, there's a close to 78% chance, still fairly high, that the sample mean will be close to the true mean. How close? Within half an ounce of the true mean. Alright, let's try to tweak the example. Let's say that instead of dealing with a 6-pack of soda, we're instead dealing with a 12-pack of soda. What's the distribution of x bar? What's the distribution of the sample mean? Well, just like before, since the underlying distribution was said to be normal, we know that the sample mean x bar is normal no matter what the sample size is. Thanks, central limit theorem. Again, we know the mean of x bar is always the mean of x, so it's still 12. The only thing that's changing is the standard deviation of x bar. A larger sample means a smaller standard deviation. So the standard deviation is now 1 over the square root of 12, our new sample size. Again, with a little bit of rounding, that rounds to 0.29. So, what is the probability that the sample means between 11.5 and 12.5? Now, before we go to the next slide and answer this question, let's think about it. Do we expect this answer to be more or less than the 78% that we got before? Perfect. We expect it to be more, right? We intuitively think that a larger sample size has more information. Having a larger sample should be better. Agreed? So what does better mean? It means that it should be more likely to be that close to the true mean. The sample mean should have a higher probability, a higher likelihood of being within half an ounce of the true mean, which means that this probability we're looking at should hopefully be larger. Sure enough, right? If I set up this problem, normal CDF, Lahore University Managerial Sciences. Just like before, the only thing that's changing is that S. The standard deviation has changed because of our larger sample size. It is no longer 0.41, it is now 0.29. Plugging all that information into the normal CDF function in our calculator gets us 0.9153. 0.9153. Which is saying that if our sample size was 12, we would have a very high probability. We would have a 91.53% chance that the sample mean would be within half an ounce of the true mean. Alright, new example. Let's say that we know systolic blood pressure for patients with hypertension or a particular stage or type of hypertension, that these patients on average have a systolic blood pressure of 140 with a variance, I throw a little bit of a curveball at us, with a variance of 25. And let's say X is the systolic blood pressure, SBP, of a randomly selected patient. Now, before I go to the next slide, let's make the observation that the calculator is always wanting the standard deviation. The standard deviation is the square root of the variance, the positive square root. So in this example, right, I told us the variance is 25. We need to be able to infer from that 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 means the standard deviation is the square root of 25, which is 5. Now, What's the probability that X, the systolic blood pressure of a single patient, is between 138 and 142? Now, what I like to do in a non-online classroom is I like to let the students work for a while, they solve it, they give me an answer, and then I cross out the answer and I write -5 points next to it. And I say, why did I mark it wrong? How would you solve this problem? You're probably drawing your normal curve, you're centering it at 140, you're using the normal CDF, 138, 142, 140, standard deviation is 5. Wrong. Why is it wrong? It's a little bit semantics, but it's important. It's important because it underscores why the central limit theorem is so great. I never, in the previous slide, said that systolic blood pressure follows a normal distribution. In reality, it probably does not follow a normal distribution. So, in the face of ignorance, I generally cannot answer a question like this. There's not enough information. I need to know the probability distribution of X to answer this question. I was not provided the probability distribution. So this question is unanswerable. IDK. That's the world that we live in. That's the world of uncertainty. That's the world of ignorance. Without making often unrealistic assumptions, we cannot answer questions like this. However, let's instead consider a sample of 100 patients, and let's consider their sample mean systolic blood pressure. Let's consider X bar. It will turn out that I can answer the probability that X bar is between 138 and 142, even in the face of real-life ignorance and uncertainty. The central limit theorem says it doesn't matter. The central limit theorem says, who cares what the underlying distribution is? The underlying distribution in this example is not known, or at least it wasn't told to us that it's normal. This doesn't matter though, right? Because the sample size is 100, and that's more than 30. Any time the sample size is more than 30, the miraculous central limit theorem says that the sample mean X bar is close enough to normal that we can conceptualize it or treat it that way. What's the mean and what's the standard deviation? Well, the mean of X bar is the mean of X, so that's 140. The standard deviation of X bar is the original standard deviation divided by the square root of the sample size, so that's 5 over the square root of 100. We get 0.5. That's the power of the central limit theorem, and I cannot begin to describe how incredible this is. I know it seems a little bit silly the way I go on about it, but I promise you, the deeper you study it, the more you'll realize that, yeah, I like to make a joke here and there, but at the end of the day, I'm actually quite serious when I talk about what an incredible theorem this really is and how powerful it is. This central limit theorem is the entire foundation of statistics, and it's pretty cool that you get at least some exposure to that in a beginning introductory statistics class. So, whereas before, I could not answer the question as to what's the probability that a single patient's blood pressure would be between 138 and 142, we will see that I can answer the question, what's the probability the sample mean is between those numbers. So here's our picture. X bar follows a normal distribution, so I drew the bell curve, centered at 140. The probability I want is normal CDF, 138, 142. The mean is 140. Remember, standard deviation of X bar is 0.5. If I do this, I get 0.9999. Darn close to 100%.
All right, which is basically saying what? It's basically saying that for a sample of 100 patients, there's a 99.99% chance that the sample mean will be within 2 millimeters of mercury of the true mean. Again, for a sample of this size, which is not that large, for just 100 patients, if you take 100 patients and you want to use that sample to try to figure out what like the true mean is for some new medication or some subpopulation, Well, if you just use a sample of 100 patients, it's virtually guaranteed that your sample mean is going to be within 2. It's going to be close. How close? Within 2 millimeters of mercury of the true mean. Which, again, just to point out, very clearly, very explicitly tells us, answers that question, how good of a best guess is it? When we say the sample mean is a good guess for the true mean, here we can see exactly how good of a guess it really is.